Okay, now we're going to have some fun with integrals. First off, I'm going to give you this funky function f of z equals sine of z over z plus 1, z minus 2, and z minus I. And I'm going to draw the minus 1 bad point, the 2 bad point, and the I bad point. Now, I'm going to give you a really funky gamma here. There's my gamma. And I'm going to ask for the integral of this f of z dz over gamma. Well, first off, I'm going to decompose gamma into two pieces. This intersection here, I'm going to create this gamma 1, and then this gamma 2. And so this integral here will now be the integral of gamma 1 f plus the integral of gamma 2 f. Now, we're going to use a standard technique over and over again. It relies on the homotopy between curves and whether or not a function is holomorphic in a region. So first off, this piece right here, if you notice, I'm going to make a region G, which is just a little bit larger than this. So there's my region G. And this function f, well, it's had trouble at I. So I'm going to write it the following way. I'm going to write it as the integral, and in the numerator I'm going to put sine of z divided by z plus 1, z minus 2 over z minus I dz. Now, this function is holomorphic in that region G and its interior, and we have z minus I with a point in the inside, and I'm now going to claim that gamma 1, this integral, is equal to a circle, centered I of radius r, that I've picked sufficiently small so it fits inside. So this circle is inside of gamma 1. And now we can use Cauchy's integral theorem. And that says we just plug in 2 pi I times the sine of I plus 1, I minus 2 is that value. Now, we're going to continue on with this piece. Now, this piece looks like this. Minus 1, 2, I. And our gamma goes all the way around it. So we're going to pick up with that. Now, I'm going to do a little trick. So first off, I'm going to start at this point, and I'm going to go up, and come back along the same line, and I'm going to have this route, called gamma 3, and this route, called gamma 4. So now the integral of my function over gamma 2 is going to be the same as integral of my function over gamma 3 plus gamma 4. And now you're starting to see a pattern. Let's look at minus 1 portion. There is a region where on the gamma 4 portion that I can now write this integral. And now what I'm going to put in the top is not going to be the same thing. I'm going to put sine of z, and I'm going to put the z minus 2 and the z minus I in the top, and I'm going to write z plus 1 in the bottom, dz. And so this integral is a holomorphic function on the interior of that G, but I'm going to pick some circle centered at -1 that is inside of that region. And so this integral, by the Cauchy integral theorem, is sine of -1 minus 3 -1 minus I times 2 pi I. Because this gamma 4 was homotopically equivalent in the region where this function is holomorphic. Therefore, that's the answer to that integral. So now we're down to this. And what's that one look like? Well, we've got this funny looking curve, and here's I, and here's 2. And now we're doing the integral of f over gamma 3. And we're going to pull the same trick again. Now we're going to cut this up, cut this back, and this will be the integral, and this will be gamma 5 and gamma 6. And now we continue. So each of these pieces are done exactly in the same way. We decompose it